So this is the hands-on for Unit 2, Q-Learning with Frozen Lake V1 and Taxi V3. So in this notebook, you'll code from scratch your first reinforcement learning agent playing Frozen Lake using Q-Learning. Share it to the community and experiment with different configurations. Here's an example of what you will achieve in just a couple minutes. So it's a GIF where this little elf is walking through a frozen lake and gets to the present. Awesome. And then there's a taxi cab one as well. Objective of this notebook, be able to use Gym, the environment library, be able to code from scratch a Q-Learning agent, be able to push your trained agent and the code to the hub. Awesome. This book is from the Deep Reinforcement Learning course. That's the one that we're taking. In this course, in this free course, okay, so this is just more info about the course. Prereqs, we just did that. Okay, a small recap of Q-Learning, perfect. So Q-Learning is the RL algorithm that trains a Q function, an action value function that contains as internal memory a Q table that contains all the state action pair values. So given a state and an action, our Q function will search into its Q table the corresponding value. Perfect. When the training is done, we have an optimal Q function, so an optimal Q table. And if we have an optimal Q function, we have an optimal policy, since we know for each state what is the best action to take. Okay, here's a link between the value and policy. The optimal policy of any state S is the argmax of this Q optimal at the state action pair. So finding an optimal value function leads to an optimal policy. But in the beginning, our Q table is useless since it gives arbitrary value for each state action pair. Most of the time, we initialize the Q table to 0 values. But as we explore the environment and update our Q table, it will give us better and better approximations. So here you see a previous example of a mouse with a single cheese, some poison, and then some triple bonus cheese. Right? The mouse can go left, right, up, and down. And as you explore, you take this action and state pair and you update it to new values based on that reward function we've seen in previous slides. Right. And you can see it right here. This is the pseudocode, and you can see that you repeat and you continue to take actions on this epsilon greedy step. You take this action, and then the Q, the value here updates based on the learning rate times this factor, and the factor is reward t+1 plus gamma, and then the max Q value of this state minus the state at t. Okay, so let's code our first reinforcement learning algorithm. To validate this hands-on for the certification process, you need to push your trained model to the hub and get a result of more than 4.5. So this is only for the taxi one, I guess. To find your result, go to the leaderboard and find your model. How do you find your model? You name your model? I guess you could find your username, and then that has a model. Look at that later. Install the dependencies and create a virtual display. In this notebook, we'll generate a replay video. To do so with Colab, we need a virtual screen to render the environment and thus record the frames. Okay, so I'm going to install this requirements. Yep, that's fine. And then I'm going to run these as well. ffmpeg, virtual display, going to need those. Make sure the new installed libraries are used. Sometimes it's required to restart. Okay. I'll run this right after. I'll just pause this as it loads. Okay, it's done loading. I will kill this. So os.kill should crash. Okay, it crashed for an unknown reason. Okay, let's see if this virtual display works. It's there. It's starting it. Great. So import these libraries: numpy, gym, random image io, os, tqdm, pickle, and tqdm. Has a number of critical issues, such as reset and stop functions are called before returning to the environment. It's recommended. Okay, it's recommended we downgrade. Let's try it, see what happens. So create and understand frozen lake environment. A good habit when you start to use an environment is to check its documentation. We're going to train our Q-learning agent to navigate from starting state S to goal state G by walking only on frozen tiles F and avoid holes H. We can have two sizes of environment, a 4x4 and an 8x8. The environment has two modes, slippery equals false. The agent always moves in the intended direction due to the non-slippery nature of the frozen lake. If slippery equals true, the agent may not always move in the intended direction due to the slippery nature of the frozen lake. Ooh, that's interesting. That's new. Okay, so let's keep it simple and do 4x4 and non-slippery. Oops, did I... to do, use the correct parameters. Okay, so this by default is failing because it doesn't have the correct parameters. That's weird. Oh, I see. So this is interesting. Okay, so I guess there's two problems. One problem is Jim has been deprecated, and I think there was a message in the Discord about it, so I wonder if there's an update. And the second problem is that there are things that are missing in here, and that's supposed to be a problem for the for us, I guess. And we can pass a random ID, and let's see what happens. So int is not iterable. Why would your ID need to be iterable? Okay, just gonna pass one called myID. MyID doesn't exist. Oh, I'm crazy. You probably need to actually choose the environment. What is the solution? Do I run this? Oh, right. Oh, I get it. Okay, so these are actually the right parameters. Just keep that. Hide solution. Oh, right. Okay, so I think if we look at this documentation, maybe if I stay in Gym, it should be fine. But to start this, it's these arguments and use to specify a custom map for Frozen Lake. I don't really need a custom map for now, but perfect. So I got that. So let's see what our environment looks like. We can print. So here we print the observation space. The observation space, 16 units, I guess. And then if I sample a random observation, it's just this one. Let's look at the documentation and look at what observation space is. Okay, so the observation is a value representing the agent's current position as current rows times number of rows plus current column, where both the row and column start at 0. For example, the goal position in the 4x4 map can be calculated as follows. 3 times 4 plus 3 equals 15. That's really strange. So why would it be plus 3? Okay, so if it's so it's the last column, and it's 3 times 4. So the current row is 3. I wonder why the current row would be 3. This person's current row is here. Oh, okay, so so the current row times the number of rows. Yeah, so the number of rows is 4. And the current... Why would it be 3? Oh, sorry. So yeah, because it's 0 index. So 3 is here in this corner. So row 3, row index 3, and column index 3 is here. 4 is just the number of rows. The number of possible observations is dependent on the size of the map. For example, a 4x4 map has 16 possible observations. It's a bit of a strange way to bit of a strange way to create an observation space, you know? So 0, 0 here would be 0 times 4, which is 0, plus 0, which is 0. If you go down 1, this would be the current row would be 1, so it would be 1 times 4, so it would be 4, plus the current column, which would be 0, so it would be 4, and then so the observation space for this first column would be 0, 1, no, 0, 1 times 4, 4, 2 times 4, 8, 3 times 4, 24. Wait, sorry. It would be 0 times 4, 1 times 4, 2 times 4, 3 times 4. And then the in-betweens would be these columns. Wow, what a weird way to do an observation space. Okay, it's interesting. Right, so the sample observation here is 1. So this would mean that you're in row 0, column number index 1, so you'd be here. So we see that the observation space, discrete 16, that the observation is an integer representing the agent's current position as current row times number of rows plus current column, right, where they're both 0 indexed. For example, the goal position of 4 times 4 map can be calculated as to follow, and it's 15. The number of possible observations is dependent on the size of the map. For example, 4 times 4 map has 16 possible observations. For instance, here's what state 0 looks like. Okay, so given that action space is 4, up, right, left, down, take a random action. So, I don't know if this is up, so yeah, right here, left, down, right, up. So this random action would be going up. The reward function is to reach the goal is 0, to reach the hole is 0, reach frozen is 0. Okay, so as long as you get to the goal, we're good. So create and initialize the Q table. Step 1 of the pseudocode. Step 1, there's no steps here, but probably this, initialize right here. Oh, here it is, step 1. Yeah, initialize right here. And then we repeat steps 2, 3, and 4. So it's time to initialize our Q table. To know how many rows, states, and columns actions to use, we need to know the action and observation space. We already know their values from before, but we'll want to obtain them programmatically so that our algorithm generalizes for different environments. Jim provides us a way to do that. env.actionspace.n and env.actionspace.n. Right, so the state space, there are, how many possible states? I believe this should be observation space, right? Okay, so there's 16 possible states and 4 possible actions. And then for this one, it's 4 possible actions per each space, because in every space you have the same actions available to you. Although sometimes you're on the border, we won't think about that right now. So let's create a Q table of size, space, and action space, and initialize each value at 0 using NP0s. NP0s needs a tuple. Okay, so let's just think a little bit ahead of what NP0s is. So NP0s takes a tuple, and let's say NP0s 2, 2, this should return to us a little box, right? 210, this should return to us. So here, 210, it's 2 rows, 10 columns, right? So what we're going to want is we're going to want, NP0s of, let's say, state action, or state space, action space. And let's print this so we actually see what's going on. Great. So now we have what we want. We have rows and columns. What is a row and what is a column? So the number of rows is the number of states that are possible, and the number of columns is the number of actions that are available to us, right? So here are state and actions. What is the solution? Oh, and they're just doing the same thing as we did. Okay, so we defined the greedy policy. Remember that we have two policies since Q-learning is an off-policy algorithm. That means we're using a different policy for acting and updating the value function. So the epsilon greedy policy is the acting policy, right? Sometimes we explore, sometimes we exploit. The greedy policy is the updating policy, right? This is that max Q star that you see in the algorithm. Oh yeah, it's right here. So this is the greedy policy, right? You always take the max. So the greedy policy will always also be the final policy when the Q-learning agent will be trained. So the greedy policy is used to select an action from the Q table. I think this is, yeah. So this is like after training, like it's always gonna exploit, right? So off policy, using a different policy for acting and for updating. On policy, using the same policy for acting and for updating. Okay, so the greedy policy, exploitation. Take the action with the highest state action value, right? So given that you're in a state, right? So if you're at any given state, let's say you have these zeros, right? You're at any given state, you want to take the maximum of these rows here, right? So the action that you're going to take is the index where this is a higher number. So let's say, first row, this is 0. Imagine this is 10. Imagine this is 100. Imagine this is 1,000, right? 1,000 is the highest value, so you want to take this 1,000, right? But you don't want to return to 1,000. You actually probably want to return the move, right? Whether this is up, right, left, or down, you want to return what it is, right? Okay. So let's say we're given a Q table, right? So let's just use this one right here. So this is the Q table, right? Let's say we're given the Q table and we're given the state. So the state is, let's say it's 0, right? So the state is 0, and this is the value of all the actions at 0. Right now they're zeros, but imagine they're not, right? What we want is the max number of this. We want the index of the max. I'm not sure how to do that, but in Python it would be something like index of, max, something like that. So how do we get the max? We probably can get the max through something like this. It's going to be a 0, but this is how we get the max, right? So, max value would be something like this. So this is the maximum value of it. And then maybe we can take an index of this max value. I'm not sure if Python has an index of, but, index of max value is essentially what we want, right? Like, what is the index that makes this the maximum value? So it doesn't have an attribute index of. Let's just search Stack Overflow really quickly. Interesting. Okay, so this is where it is. np.where, right? So let's say dot where. What is v here? I guess v is the v is the row here. Huh. So because they're all 0, this is just going to return every row. So maybe I could do it first. Tuple has no attribute first. Okay, so maybe I just index it with a 0. how do I just get the first one? I figured this one would work because I'm just indexing it with 0. I'm going to delete this and go down to where we're supposed to do this code. And I thought this is where okay, I'm going to look at the solution and see if it matches. Okay, so argmax, that's way better. So I'm taking this. It looks like this one's taking a copy of this list. So let's just double check. What is that? So this is what I had before. 0 was my state. So this is what happens there. I want to see what this does. Okay, it just makes a copy. Okay, so argmax looks like a really helpful function. And if you look at the documentation for NumPy, we can see what it does. So it returns the indices of the maximum values along an axis. Okay. So look, we are max A here. So 0, 1, 2, 3, 4, 5. Okay. Perfect. I would think that you'd want to only take one of them, but it's interesting to me that you wouldn't want to only take one of them. But let's see. Okay, so we have our greedy policy. So we learned something today. We can use argmax here. So epsilon greedy is the training policy that handles the exploration and exploitation trade-off. The idea with epsilon greedy is, we do exploitation and exploration based on some probability, right? Great. So randomly generate a number between 0 and 1. Okay, I'm going to copy this. This is how you do it in NumPy. Learn something new. Random.uniform. Actually, I don't think this is NumPy. I think it's just regular Python, right? I think random is a Python package. Import random. Yeah, so random is a Python package from the standard library. Okay. So if the random int is greater than epsilon, exploitation. So take the action with the highest value given the state. Argmax can be useful here. So we do the greedy policy. So this is the complete greedy policy, and here's the action. I also do exploration. So we do an env.actionspace.sample. And return that action. Okay, so the action is greedy policy, where we pass in the Q table, and it's a state. And then taking a random action would be from the environment, we sample an action. Okay, great. So we define the parameters. The exploration related hyperparameters are some of the more important ones, some of the most important ones. We need to make sure that our agent explores enough of the state space to learn a good value approximation. To do that, we need to have progressive decay of epsilon. If you decrease epsilon too fast, too high a decay rate, you take the risk that your agent will be stuck, since the agent didn't explore enough of the state space and hence can't solve the problem. So here's some training parameters. We have 10,000 training examples. We have 0.7 learning rate. Our evaluation parameters is 100. Here's our environment. Max steps is 99. Gamma is 0.95. Evaluation seed is empty for some reason. We have a max epsilon, a min epsilon, and some decay rate. So we create the training loop method. Okay, so the training loop goes like this. For episode and the total of training episodes, reduce epsilon, since we need less and less exploration. Reset the environment. Okay, and then for step in max time steps, choose the action at epsilon greedy policy. take the action A and observe the outcome state, state prime here, and reward. Update the Q value using the Bellman equation. And if done, we finish the episode. Our next state is the new state. Alright. So here we have some code, and I think it's this thing above. So for the definition of train, we have some training episodes, min, max. Okay, so these are the hyperparameters that we define above. So for the episode in TQDM, I don't know what TQDM is. Oh, interesting. Yeah, it's a progress bar. Did not know that. Never used that before. Okay, so reduce epsilon because we need less and less exploration. So the min epsilon plus max epsilon minus min times MP exponential decay times episode. Okay, so that's new epsilon. So epsilon is being decreased. Reset the environment. State equals environment that resets. Step equals 0. Done equals false. For step in range of max steps, choose a policy of the epsilon greedy policy. So we had an epsilon greedy policy here, and it took some arguments, and the arguments were the Q table. So passing this Q table, the state. So whatever the state is here, I guess, and an epsilon. So the epsilon is probably the epsilon that we have above. So we take action A and observe the reward and the new state. So take the action A and observe the outcome, state, and reward. So I believe it's some environment, and we have to, I think we take a step, and we step through, and we're going to get certain things back. And the action that we're taking is this action here. So this is the only argument here. And it's returning a new state, reward, done, and info. So we want to update it, so we're going to use the state and action to index into this thing, and then we're going to update it with this thing that we have here on the left side, right? So we have a Q table at the state and action, plus the learning rate here. So the learning rate is where's our learning rate? It's not the decay rate. Where's our learning rate? I'm just going to put learning rate here. It's going to be undefined, but just figure that out later. The rewards, the reward that we got here, plus this gamma. Where's our gamma? I'm just going to put gamma here. It's going to be undefined. Times the max of this other thing, right? So this other thing is the greedy policy. Do we have a greedy policy? We have an epsilon greedy policy. We have a greedy policy, right? So we're going to use the greedy policy, which is just going to take the maximum. The greedy policy will take the Q table, and it will take the state, and then we will subtract, what's currently in there, which is the Q table at this state and this action. And if it's done, we finish. Okay. And our next state is the new state. Right, so the state is reset to this new state, and then at the end of all these, so after all these training episodes, and there's going to be 10,000, I believe. Yeah, so this Q table starts off as empty, and at the end of it, we will everything will work. So we're actually missing the learning rate. I'm going to see what they use for learning rate here. They just use learning rate, but where was learning rate set? I don't remember setting learning rate anywhere. This is below. Oh, okay. So learning rate is actually just set here, and gamma is set here. Okay. So learning rate should be learning rate. Perfect. Okay. I'll just do a spot check. So action equals this, new, yep. Emp.step equals taking an action, yep. We did that in the last collab. This equation, qtable state action plus learning rate times reward plus gamma times, they use np max. Why do they use np max? Why do we make the greedy policy function if we're not going to use it? Strange, huh? Anyway, they use np max and then they subtract it by qtable action. Okay, so everything is the same except for this greedy policy, which is what we wrote above. And they use it here in the evaluate side. Okay, I'm going to keep my version and see if everything just works out, because we made greedy policy for a reason, and here they're doing the greedy policy manually, but that's fine. Everybody can choose their own way to do greedy policy. Okay, so let's try to train this. Okay, end training episodes is not defined. It's because I probably didn't run this then. Okay, so I run that cell, and then I can run this cell. Well, I didn't have to run that cell again, but then I can run this cell. So that variable is now defined. Ooh, look at that progress bar. I'm starting to like the progress bar. It's very nice. Awesome. Okay, so the return value of this train function is the qtable. So if we just run this function, or just run this, we'll look at the qtable. The qtable is mostly empty, but these things are very valuable. And what are these things? This is the so this is the value at this particular location. So this state and action pair. Which state is, what is this? 15. Which state is 15? 15 is, so which one of these is 15? 15 is, it's right here. So the goal position is 15. So maybe this is not 15. What is this space? Yeah, so reinforcement learning is really strips out the human component of these calculations, puts them into these tables, at least this qtable method, and makes it so the computer can calculate really without the story, without the narrative of what's going on here. So there's 16 total rows here, and in terms of index, this is index number 14. What does that mean? It means index number 14 is this position right here. It's this position. So when you're in this position, you're in row index 2. 2 times 3 is 6. And you are in column 3. So that would be 9. When you're in this position, you're at 3 times 4, which is 12, plus 0, 1, 2, 14. So 14 is where all the value is when you look at this map, right? In no other position are you one step away from the present, right? In this position, you're in a puddle, you lose, game over. In this position, you can't go diagonal, so you can't go to the present yet. So this is the only position that is valuable, that's one step away. Now, we're not decrementing reward based on time, right? So you could actually go on forever, You can reach ice forever. You can look good, you know, you can go down, up, down, up, down, up, down, up forever. And you're just going to get 0 reward. There's no negative punishment for taking too long. There's only a positive reward for reaching the present. So if you look at this and you think about that map that we just looked at, right? It's really hard to do that as a human. So is there a way we can just okay, so this is looking at it, right? So this is 14. This is that position, and the actions are here. Now, which action is going to the present? Probably this action. It's the highest one, right? I'd imagine that this is the action for going right. It's 2.9 reward. What is going right? Going right is 2. So 0, 1, 2. Perfect. So this is, 0, 1, 2. So this is going right. This is going to get the present. What is the reward for getting the present? The reward for getting the present is reaching the goal is +1, right? So a lot of +1s are being added to this. A lot of +1s times everything else, right? Times this, right? Where the reward is here, and it's going to be 1 plus gamma, whatever, the other stuff, right? Times this learning rate. So a lot of +1s are going on here. Okay, great. So let's evaluate this agent. So we have this agent. It's got all this stuff. So the evaluation is, resetting the environment, making it only do the greedy policy, only do the greedy policy, only do the greedy policy, and then accumulate these total rewards, and then return the mean reward, standard deviation reward. So let's evaluate our agent. The mean reward is 0, plus minus 0. Something's wrong there. Definitely should not be 0. We should have a mean reward of 1. That's for sure what we should have. So it's a bit strange. I'll admit, it's a bit strange. We have a mean reward of 1. So we had this. Huh. Very strange, very strange, very strange. Why would it be a mean reward of 1? So the only thing that I can think of is we have, for all these state action pairs, when we have 0 across the board, at least the way that I read the code, we're getting, in this action here, we're getting a list of options. Does this env.step take a list of options? Or can it only take one single value? Like, what does np.max do here? That R thing. Let's just switch it and see what happens. But I feel like these should do the same thing, right? In fact, you can just check it. So np.max, let's just create an array where, it's this. So the max is 4. Now, let's do greedy policy, and this takes 0. This probably has to be a nested, yeah. So this needs to be nested. Okay. Okay, so our greedy policy is returning an index. This greedy policy function returns an index of the highest amount, whereas this np.max is returning the value that's the highest amount. So this one's actually correct, because we're not. So the greedy policy returns an action, and this returns a value. They're both, they're both integers, or floats, but this is the correct one. We want to return the value, right? This is the max value at Q of the state action pair. Okay. That makes sense. That makes sense. Because the index means nothing, actually. The index means nothing to this value function. The index only means something to this environment, right? It only means something as an action. Okay, perfect. So let's run this one now instead. Let's close the solution. So let's train again, and let's see how our table differs. Our table is going to be different. Okay, so now this makes a lot more sense. This makes a ton more sense, right? Because this position is what we wanted. This position is what we saw as the position that's to the left of the present here, right? It's to the left of the present. Present is 1, so you get, reward is 1. It looks like it converges on that 1. And then everything else is, Bellman equation style. Further and further away from this 1, there is some decay. But at any one of these positions, you can see, taking the optimal greedy policy, you go closer and closer to the higher value. Okay, so now we evaluate our agent. Because this makes a lot more sense, because in the beginning, being in the first state and everything is 0, it's like you almost take no action. Okay, so let's evaluate our agent. Our agent is mean reward is 1 plus minus 0. Great. So publish our train model to the hub. One line of code. Here's an example model card. I'm not sure what a model card is, but let's push this. That's not the line of code. So record video. Cool. So this records a video using the image IO package. This is publishing to the hub. Okay, cool. I already did that. Sign in, you need to store your authentication token. Okay, so let's log in. Okay, I'm gonna pause this and put this token in. Okay, great, so my token's in there. So we create a model dictionary of these hyperparameters. Perfect. And let's fill the push to hub function with the repo ID, the model, the environment, and commit message. Perfect. So this is the model. This will be used in the model card. The username. I'm not sure what my username is. Let me be right back and fill this out. Okay, that's my username. And push the hub. Awesome. Perfect. So great. Now I have a model here, and here's my little elf guy. Awesome. Perfect. Great, great, great. Okay, congrats. You've implemented from scratch, trained, and uploaded your first reinforcement learning agent, Frozen Lake V1. No slippery. It's a very simple environment. Let's try a harder one. Pausing it and starting a new video.